Okay, students, we're going to continue talking about Newton's law of universal gravitation, and I'm going to bring back maybe an older topic for you, and that's the idea of a force field. Okay, we're going to get back to vectors. They never really go away. Okay, remember that a force field is a region in space where something experiences a force. It's a vector field. Okay, so in this case, I'm showing field lines going radially outwards away from this whatever this thing is. We don't know what it is. It doesn't matter. But this shows a force, a field emanating outwards. Okay. Now, in this particular class, we study three different kinds of fields. Gravitational fields. This is a region where a mass experiences a gravitational force. An electric field is a region where a charge experiences an electrical force, and a magnetic field is a region where a moving charge experiences a magnetic force. And fields can be represented by sets of three-dimensional vectors going in all directions, pointing in the direction of the force. So, for example, a gravitational field, you know that the force of gravity acts inwards towards the center of a planet, which is the center of that sphere, okay? So we would show the gravitational field looking like this, and the implication is that this is three-dimensional in outer space in all directions, okay? All right? Turns out that, you will study this eventually, an electric field around a positively charged object emanates outwards in the opposite direction, and the electric field around a negatively charged object looks just like that of a gravitational field, and all the force, the field lines are going inwards towards that center thing that's creating the field. Okay, so this idea of a force field is universal in physics. We will be studying it. We will be talking about it a lot in lots of different, in three different ways certainly. Okay. All right. So other depictions of force vector fields. They don't have to be emanating in 3D space around a particular mass. They can be all over the place. Here's one right here. Remember the length of the vector and how close together the field lines are indicate how strong the field is. Okay. All right. Other examples of fields. Here's a circular one. Okay. It can get complicated in 3 dimensions. Right. Here's the electric field lines around two positively charged particles. That's kind of interesting. We'll study that later. All of these have things in common, and one of the things in common is that the force acting on a mass in the field at a point, if it's a gravitational field, is always in the direction of the field lines with a magnitude equal to the relative length of the vector at that point. In fact, that's true of all fields. So remember, like if I were to put a mass, let's see, let's go back to this one. If this were a gravitational field, if I were to put a mass right there, that mass would experience a net force in that direction going along with the field lines, okay? Pretty cool. Oh, and one other thing, force fields are three-dimensional. Okay, I haven't even really talked about forces yet, but forces and vector fields. But vector fields are three-dimensional and force fields are three-dimensional, okay? Now, a couple of words about 3 dimensions. We've talked about this previously, very briefly. Instead of the x and y coordinates, we have x, y, and z coordinates. So we deal with 3 numbers. Instead of x and y, we deal with x, y, and z. All of them are orthogonal or at right angles to one another. And every point in 3-dimensional space can be described as a set of coordinates in that order. For example, okay, in the 3D space, 2, 3, 2, 2 is x, 3 is y, and 2 is z. So to do this, you would go 2 on the x-axis, 3 on the y-axis, okay, 2 on the z-axis. Notice that this is coming out towards you where negative z is into the board, okay, and that is the point in question right there. Now, often it's useful to sketch a sort of a 3-dimensional box where the origin is at one corner and then the point in question is at the opposite end of that box, okay. Can get complicated in 3D. You're not required to perform 3-dimensional mathematical operations, but it's going to get a lot more complicated when we study electricity and magnetism. 3-dimensional ability is going to be crucial for your understanding of that particular topic. Again, complicated. Okay, so when working in 3D space, we need to have a way to show vectors going into and out of the board or the page. So by convention, a vector going into the page or into the board is denoted by an x. So you can think of the x as looking at the tail end of the vector. A vector coming out of the page is shown with a dot. You can think of that as looking right towards the tip of that arrowhead. Okay, all right. Here's sort of a 3-dimensional situation here. It turns out that when you run a current through what's called a solenoid, which is a bunch of wires wound tightly together like this, and the current is going in this direction, turns out that that creates a magnetic field. That is not important for you right now, but what I want to show you is how we can depict the current direction as being either into or out of the page like this. So this is looking at the side of the solenoid. You see on the bottom the current is coming towards you. Well, the current through each of these wires, which are depicted by little circles, the current's coming out, so that vector is shown by a little dot. Okay? On the top side, the current's going away from you or into the board, and that's shown by an X. How cool is that? Okay, this is going to be all over the place in this course, especially next year. Okay? All right. So the closer the field lines are together, the stronger the field. All right? And we saw before that an object weighs more on the surface of the planet than it does in the upper atmosphere because of this. Okay? Now, how does an apple, for example, above the Earth, how does it know that there's another mass attracting it, namely the Earth? How does it know that? It doesn't have a brain. How does it know that? Well, because it's in a gravitational field. And a gravitational field is a region in space where the mass, any mass, experiences a gravitational force. This gravitational force is called weight, and you know by now that W equals mg. It's three-dimensional. Okay, it's shown by all these vectors right here. Okay, all right. In the case of the Earth, there's a rock in space. A rock has mass. It's going to be pulled towards the Earth in that three-dimensional vector field going right towards the center of the Earth. Now, these things, this rock would not actually be able to get to the center of the Earth because it would hit the surface of the Earth first, and the surface of the mass of the Earth between the center and the surface would keep it from penetrating it. Okay, but you get the idea. All right. Okay. Now, from one point mass, the situation is simple. Besides there being less distance, the more mass creates a greater gravitational force, right? By Newton's law of universal gravitation. I'm going to define the gravitational field strength for you now as the force per unit mass acting on a small mass, usually called m naught, a test mass or a point mass, placed in the field. Now, in the units of little g, we call it little g, and it's not a coincidence. These are newtons per kilogram, and it's assumed the following, that m naught is so small that it does not affect the field it's in, and the gravitational field strength is given the variable little g, which, not coincidentally, again, is also the acceleration due to gravity. Now, the field strength at a distance r from a point mass m can be found by putting m naught at that point and finding the force on it, because it's the force per unit mass. So if F is gm, m naught over r squared, okay, all right, and little g is F over m naught, if I divide this expression by m naught, the m naughts cancel out, and I get gm over r squared. And this is a universal expression for the gravitational field strength, a distance r from the center of any mass m. Okay, that is the gravitational field strength. That is also the acceleration due to gravity, as you now know. Okay, what are the units of g in fundamental SI units? Again, a Newton per kilogram is the same as a meter per second squared. You see, all these things are becoming crystal clear to you. You're becoming real physicists. This is totally awesome. Gravitational field strength and gravitational acceleration are the same thing. G equals G, no matter how you slice it. Okay? The gravitational field is a vector field, and the direction of the field of vectors is the direction of the force on the mass. The direction is negative r hat. Here's your positive r hat, the unit vector pointed outwards. The gravitational field, the direction of the gravitational field is negative r hat. It is a three-dimensional force field.